Good morning and welcome to our Marposs introductory webinar series on leak testing. Today's topic we're going to look at is pressure decay. For those of you that don't know me, I'm Gene Grilly. I'm a Marposs Corporation technical specialist specializing in leak testing. I've got over 20 years of experience working with pressure decay, mass flow, mass spectrometers, assembly equipment, that type of stuff. So seen a little bit of it. One of the things is all your microphones and all the video is turned off. The only person you guys can really see right now is me. So those are my colleagues still working at home. Feel free to get back into your pajamas. After the presentation, we'll have some time for questions. The questions are in a format of text questions and that type of thing. You guys won't be able to get on the microphone or anything like that, but we'll answer any questions that you may have. Today, what we're going to turn around and take a look at are the primary test methods that utilizes. And the first thing we're looking at with pressure decay, there's really two primary methods, pressure decay and mass flow. Pressure decay is divided into two categories. We call them gauge or relative or absolute pressure decay or differential pressure decay. And then there's also mass flow, which there's two versions of that also. And it's kind of a flow and a leak test is what we take a look at on that. Let's give you a little bit of history on just the pressure decay. And what we're talking about is in the 1950s, primarily underwater testing and gauge decay. This was all manual type of testing at this point. Most of it consisted of sealing up a test part, putting it underwater, pressurizing with air and seeing it, watching the bubbles come out. In 1956, there was a study done by Ford Motor. It was done on cast iron aluminum or cast iron cylinder blocks. And the specifications that really came out of that were 12 cc's at 20 PSI. The reason that's kind of important for automotive, that really became the casting specification for a number of years. This carried well into the 90s and into the aughts. But 12 cc's at 20 PSI, and where that testing really came from was just taking these cylinder blocks and finding out where they leaked air and what was the correlation between the air leak and the oil leak or the water leak that was coming out of these. And what they established was pretty much they were able to detect these leaks at 12 cc's at 20 PSI. As long as the parts didn't leak that more with air, they felt pretty comfortable with it. In the 1960s, the pneumatic balancing came into play. And what that really did is it replaced the underwater dunk tanks and the manual gauge decay systems. And these were a little bit better systems, but they were very difficult to maintain. The primary manufacturers of these systems in the 60s and the early 70s were Beach Engineering, Turner Brothers, and Scans here in the Detroit area. And this is kind of where it started in North America. In the 1970s, electronic memory became one of the bigger topics for pressure decay. What this really did is it removed the operator from the equation. In the 1980s, we introduced microprocessors into pressure decay. In the 90s, multi-channel pressure decay options were introduced. We start talking about gauge pressure decay. This is kind of where we're talking about is involves an operator, a simple pressure gauge, a manual isolation valve, and a pressure regulator. Basically what would happen is the operator would open up the manual valve, pressurize a test part to a given pressure, shut that manual valve, and then just observe the gauge washing for it to decay. This had a little bit of a benefit over doing the dunk tank is that you didn't have to get the part wet and you didn't have to make that mess with the water, but it was still very operator dependent. And this is still the granddaddy of pressure decay systems with a regulator, an isolation valve, and then the test part. We start getting into pressure decay. This is one of the things I picked up from my colleagues just recently. And it's really a great way of thinking about pressure decay. Pressure decay is not the leak. The pressure decay is a symptom of the leak, meaning that the leak, it's not the pressure decay, it's not the air loss we're looking at. The leak is actually the hole, okay? And that's really what we're talking about. So the pressure decay is just a symptom. It's telling us what's going on because of the defect in the part. Simple pressure decay is really comprised of 3 steps. The first step is the fill step, where we turn on and pressurize the part, trying to get all the air that we can into it. So if our test pressure is 10 PSI, we're looking to pressurize it to 10 PSI. Next step, we turn on and we shut off the fill valve, so we're no longer putting air into it. We turn on and measure it. And what we're looking for right here is a gross leak at this point. We're letting things settle down a little bit. Then the third step, we get into measure, okay? And this is where we're actually determine how much of a pressure change we're seeing during the step and look for what's caused by that leak. Exhaust a lot of times is the fourth step, but it's kind of hidden because it's not always required. Some of the low pressure tests and things like that, just removing your seals will turn on and evacuate the part. So exhaust isn't there. Sometimes it just happens naturally. So when we get into early electronic memory pressure decay leak testers, the first ones really were similar to our gauge decay testers. Is we had a regulator, an isolation valve, and a transducer. The difference now is that the tester controlled the isolation valve and now was reading the transducer. So we've eliminated the operator. This gave us a little bit more repeatable testing and things like that. One of the problems, and my colleagues at Techna really stress that this is not the system that Techna uses today, okay? This was an early model developed here in North America that had a single solenoid valve. And the problem with a solenoid valve is when it developed a leak, it would turn on and keep pressurizing the test part, so you'd never see a leak in the part. But this was one of the early problems of some of the early pressure decay systems. Today, when we look at a real Techna pressure decay system, what we're looking at is a regulator. We actually have two valves now. We turn on and use what we refer to as a fill valve and an isolation valve. So the fill valve lets us put air into the part. The isolation valves allows us to cut off the air from the test part. So that if the isolation valve were to develop a leak, it would turn on and flow out of the part itself, okay? That's what we're looking at. But this is typically the modern gauge pressure decay leak test system. Simple regulator, two solenoid valves, and a transducer. One of the things that gets sometimes a little confusing, especially in terminology for those that aren't really familiar with it, is we can do positive pressure or negative pressure. When we start looking at vacuum decay systems, so a lot of times people say, can you do vacuum? And for an air test person, oh yeah, we can do vacuum all the time. But what they're really referring to is trace gas or something like that. So one of the things we look at is vacuum decay. We still have our pressure regulator. We have a vacuum source. Usually that's a Venturi vacuum system. We've still got our normal two solenoid valves and the transducer, but it's whether it's pressure or it's vacuum. The only difference is we add a Venturi to the system. One of the things I want to talk just a little bit about, I don't want to get too much into it, is what we refer to as adiabatic. And what adiabatic is, this is really the process where we're going to turn around and we pressurize the part. And as soon as we shut off the fill valves, we actually see kind of a decay. We actually see it where it looks like a leak is forming. What that really is, it's just the transfer of that energy. It didn't transfer, it's just settling itself down. Okay, this is why we have the stabilize, but the scientific term for this really is adiabatic, and we pressurize the part, and we're going to show you a little example a little bit later of what goes on with that and how we're doing it and what we do to combat it. There's really three ways you can deal with adiabatic. One is ignore it. Just make sure you have enough measurement time to differentiate between a leaking and non-leaking part. So you just turn around and pressurize your part and monitor your decay. And the big concern here is you want to be able to differentiate between a good part and a bad part, okay? Stabilize. The more time you allow it to stabilize, the less you reduce that adiabatic effect, okay? And one of the other things you'll see is that optimizing pneumatic components can have a big effect. Sometimes if you're filling a part way too fast, you can create more adiabatic than if you were using smaller pneumatic components. So bigger isn't always better. Three things we really look at when we start looking at pressure decay leak testing is part volume. How big of a part are we trying to fill? How small is it? Test pressure, is it high pressure? Is it low pressure? For most of the testing we do, it's really referred to as low pressure testing. Less than 150 PSI is normally considered low pressure. And then leak rate. Normally for us, we talk about leak rate in cc's per minute. Sometimes you'll see liters per minute and that type of thing, but normally when we're talking about pressure decay leak testing, you'll see things like pressure drop or cc's per minute as far as the leak rate goes. I don't want to spend a lot of time on this. If there's something you guys would like to see or get a copy of, go ahead and feel free to contact me. But this is what I use for calculating cycle time and things like that. And it's all built upon what we refer to as the leak rate equation. And it's just the leak rate in cc's per minute, okay? And it takes in consideration the pressure change and how long we're gonna measure for. And here in the US, I know we were supposed to learn the metric system back in the 70s, but it never really stuck. So I'm stuck in the imperial system. So I have to turn around and still think in PSI and cc's. It's just something in my brain that doesn't allow me to think in liters and KPAs. So I'm always looking for some type of correlation with that. When we start talking about part volume, what we normally see is on pressure decay, it's normally the smaller volumes. We'll see that 1 milliliter up to 7,500 milliliters. When you start getting over 450 cubic inches for pressure decay, you really want to start looking at other techniques outside of absolute and gauge pressure decay. Differential will work on it, but even then, you're starting to get in a little bit of trouble on some of these larger volumes and stuff like that, over 450 cubic inches. Small volumes, not a problem at all. Sweet spot for this is really about 125 cubic inches. That's really where this belongs at. And what you'll see is that a lot of the applications that fall in this, cylinder head and block castings, transmission worm patterns, clutches, fuel lines, these all kind of fall into that volume category. Where you start losing it at is things like gas tanks. While the test pressure and leak rates are well within range, the part volume just makes it unrealistic for pressure decay type of testing. When we get into start talking about test pressure, this is really vacuum minus 14 PSI and pressure to about 30 bar. This doesn't mean there's not pressures higher than that. It's just that that's typical is where we see this is about 30 bar. Beyond that, we start getting into some special sensors and things like that, but typical is less than 30 bar. If I had to put a bet on it, it's most applications are less than 2 bar. And the sweet spot for this really is under 100 PSI. You'll see the test pressures. These are really typical parts for the volume and pressure. These are all common because they all fit that range. We start looking at leak rate. Leak rates normally range anywhere from about a half cc to 1,000 cc's a minute. A lot of this is going to be driven by how large a part volume you are. You can have a 200 cubic inch volume and looking for a half cc a minute isn't realistic, okay? There's other techniques we can use other than pressure decay, but a lot of these start going hand in hand. Rule of thumb is the higher the test pressure, the larger the volume, the longer the cycle time. The larger the leak rate, the smaller the cycle time. But these three items, the pressure, leak rate, and the volume all go hand in hand with whether it's a viable application, okay? And sweet spot for pressure decay is really about 1 cc to 150 cc's a minute. I have done applications as small as 0.1 cc's a minute, but it was a very, very small volume at about a 20 PSI test pressure, okay? And sometimes it's just a matter of doing the application work before you turn on and commit to something like that. We start looking at typical specifications for medical. We start looking at catheters, and those are normally in the 90 to 145 PSI range with leak rates of about 1 to 20 cc's a minute. Angioplasty, those are usually a little bit higher pressure. Drug delivery, those are normally a lower pressure. You'll see the leak rates are fairly similar. Filters, normally about 1 to 3 bar. And when we start talking about package seal strength, a lot of times what we start talking about isn't so much cc's per minute, but we start looking at 10 to 20 microns as far as a hole size. So we're not looking at a flow rate there as much as we are looking just at the actual size of the defect. 10 to 20 micron comes in a lot too, is where you start seeing that in some of the automotive applications where some of the fuel components have started correlating. Instead of looking for a cc's per minute, let's look for a particular hole size in the component. So what you'll see is a 10 micron or a 25 micron hole size in some of the fuel components. But typically correlation comes out to on like brake systems, 90 to 145 PSI. Engine components, oil, water, air, anywhere from 3 to 35 PSI. A lot of times what drives this is the stage that it's built into. So you'll see castings when we're looking for porosity, the leak rates are normally smaller and they're testing at higher pressures. When we get into complete assemblies like an engine assembly or a transmission assembly, now our test pressures are like 3.5 PSI or 5 PSI, and the leak rates are much smaller, or actually much larger than what you'd see on the actual castings. We're going to go into, I want to show you guys some videos on this. And this was my actual test rig, what I was using. What you see on the left-hand side is the Tecna leak simulator. This device allows me to turn around and tune in a particular leak rate at a given test pressure and treat that as a leak master. We call it a leak simulator or an LTC. The other thing I used was the Tecna T2 leak tester. It's just a simple pressure decay instrument, pressure regulator, 2 solenoid valves, and a transducer. Then we had a test part. This is just a reference cylinder we use here at Marposs just for testing components and verifying everything's okay. But this is what the actual setup looks like. And so I give you a good shot of what the screen looked like. What we're looking at on this is
Gene, hold on a second. Your audio, we cannot hear you.
Can you hear me now?
Yes.
Okay, sorry about that. Let me talk to you a little bit about this, the seal leak test. This is a test that's 90 seconds long. It's 30 seconds of fill. We're trying to make sure that we can see the test part, that we can actually get up to the test pressure. Then the next 30 seconds, we go into settle phase where we're allowing the part to stabilize, and we're just monitoring for a gross leak. Ideally, what we're looking for is if we have a non-leaking part, there's no pressure drop. Then we get into the measure phase, and this is where we're actually looking for a fine leak. This is where we're looking for a small leak. So if you look at a reject in the stabilize step, this is a step that'll turn around and show you that you've got a real big leak somewhere. It could be a missing seal, something's not in place, but you're not looking for a fine leak during the stabilize step or the settle step. Now we're going to take a look at a part with a leak installed in it and see what this looks like. The pressure decay test is really one of the biggest troubleshooting tools you have for pressure decay leak testing. If you don't have a seal leak test built into your program, into your tester, you need to make sure you put one in. This doesn't look at what the actual cycle time is or anything else. It just slows everything down. The 30 seconds, we look at most parts can be filled within that time period. The settle phase, we're just looking for gross leaks at that point. We're just letting everything settle down, getting rid of that adiabatic. Then when we get into the measure phase, it really is a fine leak. So what we should be seeing during that measure phase is the actual, what's caused by the leak step itself, okay? And that's really the seal leak test. It's a big troubleshooting tool. And the Tecna testers here in North America, it's always the last program in the tester itself, okay? There we go. This is the one with the leak in it. Now what you're starting to see is a little bit of pressure drop, okay? And this is kind of what you'll see, but right now, is it adiabatic or is it caused by the actual leak, okay? Kind of cheated a little bit here telling you that it has a leak in it, but this is what we did is we installed a 2 cc per minute leak, and we're looking at the actual pressure change that's going on for this step. And so what we're seeing, this pressure drop right here, this is what's caused by that 2 cc's being installed. We know we've got a pretty good part because we looked at the last test and it showed us that we didn't have a leak. Now what we're seeing when we look at this is we had a delta P without the leak, pressure change reading of 0.000, and delta P with the 2 cc's was 0.042. So you can see that that was the effect caused by inserting that leak into the system. Now what we want to do is take a typical pressure decay test. We're going to shorten the cycle time down a little bit. We're going to only have 5 seconds in the fill, 5 seconds in the settle, and 5 seconds in the measure phase. And we'll take a look at this. We're pressurizing the 10 PSI. You can see our fill in here. Our time counting down. We're in the settle phase. Then we go into the measure step. So this is what our test looks like with a leak, okay? We had a pressure drop of 0.035. Now we go to our pressure drop with no leak and look at the pressure decay on this. We're gonna fill the part up. We're settling, but you still see that drop there? That's really the adiabatic. That's not caused by the leak. That drop that we're seeing during the settle and the measure right now, this is really the adiabatic, and this is the effect. So it does look like it's leaking, but it's really just the adiabatic, okay? So when we get to that, what we look at is the delta P using this cycle time, the 5 seconds fill, the 5 seconds settle, and the 5 seconds measure. We see a pressure drop without a leak of 0.028. That's all adiabatic, okay? The 2 cc leak caused a pressure drop of 0.035. It's really only a difference of 0.007 PSI caused by the leak master, okay? And this is the effect of slowing the test down, okay? Next, I want to show you is what happens if you extend that fill time out, okay? And this is one of the mistakes people will do is they turn and look at a leak tester and they go to speed it up. And they see that it reaches the fill in 3 seconds and it's got a 5 second fill in it. So they'll take that 2 seconds out and wonder why the repeatability goes away. Well, once the part reaches the 10 PSI, it's really stabilizing. Even though it's still in the fill step and those fill valves are opened, it's really settling down during this step. So what you see during the settle phase here, that's still 5 seconds, and you can see our actual leak step with a leak rate 0.008 PSI. Okay, during that 5 seconds, very similar to what we saw the difference was before, okay? So this is it with a leak. So this one, we're just gonna turn on, keep the fill at 5 seconds, but we're gonna extend the stabilized time out to 25 seconds. And watch what happens as this thing settles down. You start seeing everything kind of slow. The drop is there. And this is with no leak rate installed, okay? Some of the challenges when we start talking about pressure decay are temperature. And temperature has a few different characteristics. One is it can be background temperature, plant air temperature. Some of the facilities I've dealt with, temperature starts out rather chilly in the morning, and by late afternoon or early evening, it's very warm. So you'll see some background temperature that can impact pressure decay. You also start seeing changes that are caused by part washers and processes that'll actually heat that part up. So temperature is one of the big challenges with pressure decay. When we're looking at pressure decay, what we really want are clean, dry, and ambient temperature parts. We don't care what temperature it comes in, just bring it to us consistent. And I know a lot of times that's easier said than done. Part material, this can play a big factor in doing the test. Some of the plastics and the aluminums and things like that have different porosity than cast iron. So sometimes you've got to be aware of what your material is doing. Some of the medical devices, the material is rather thin walled and that type thing. So what you'll actually have is some ballooning. When you start getting into some of the collection bags and things like that, we actually turn around and contain those products to limit the amount of growth they have for expansion. Test air quality. This is an important one. We really want clean, dry air. It needs to be filtered. Years ago, I worked at a plant that the air system ran outside. So in the winter here in Michigan, we'd pick up an awful lot of moisture from the changing temperature of the air as it ran through the plant and that type of thing. And it just created all types of havoc as we were putting moisture into the test process. Sealing system, this is a big one. If you can't seal the part, it doesn't matter how good your tester is, you're not going to be able to pick up leaks. Your sealing system has to be able to repeat and be able to do it reliably time after time after time. Cycle time. A lot of times, cycle time is driven really by the characteristics. How large a part is it? What's your leak rate and what's your test pressure? Because you only have room for one test station. If cycle time requires two, that's what you're going to have to do. It always works that way. You just can't squeeze out cycle time because you want to, okay? Repeatability and reproducibility. This is a big one. It really started in automotive, but we're starting to see a lot more of this in the medical community as far as being able to repeat what you do and be able to reproduce the leaks and things like that. So repeatability and reproducibility, really a big one. We use a product here at Marposs called Quick SPC for data collection and that type thing for analysis. And we're able to run these gauge R&Rs and things like that with that. One of the other things you want to look at is elevation. Sometimes we've had facilities where they're trying to do comparisons with elevation and they're trying to figure out why they get different results in this location to that location, and some of it's due to elevation. Another thing that's really a concern on pressure decay is common wall leakage. If you've got two cavities that are being pressurized both to 20 PSI, and they're both running the exact cycle time, you may not pick up any leaks between the two cavities, okay? I want to start talking a little bit about single channel leak testing, and this is what we're referring to is our normal pressure decay system, pressure regulator, 2 solenoid valves, and a transducer, okay? And this is a typical single channel configuration. One of the things we start looking at are catheters, where we would just use a simple pressure decay test, okay? Cap off one of the lines, bring air in, probably have a lure connector right here, and be able to do this as a quick medical leak test on a catheter. Collection bags, this is the one I was talking about where we actually constrain the package. We turn around and, because this blows up like a balloon, we actually put this between two plates to do a leak test. This particular fixture is a 2-channel fixture, meaning we can test 2 parts. And if we're gonna do that with single channel testers, we would have 2 testers to do that, okay? That allow you to run them asynchronous. Load one, test it, unload the other, and then test that one, okay, and just keep them running that way. So a lot of times this will be a typical medical single channel configuration. But we can also do the same thing with a dual channel configuration. One of the things you'll note is we've got 2 leak master ports on the front, but now we can load 2 parts, hit a single start button, and both parts are tested at the same time. And this is what we refer to as a dual channel. One of the things on single channel, we started looking at automotive. We can get a little bit more creative. One of the applications I worked on previously had a fill step, settle, measure, and an exhaust. Then the PLC took over and did an oil fill, all with the same sealing tool. And program 2, we actually did a volumetric check to turn on and verify what the oil fill was to. We were double checking the oil fill system, and that's what this was for. And the way the engineer explained it to me is we know that the operator put oil somewhere. He just wanted to make sure it went into the axle. Okay, so we did that all in the same tool. It's actually a pretty slick system for that. One of the other things we start seeing with single channel testers is exercising it. On automotive clutches, a lot of times what they're trying to do is there's a seal that's in there that we turn around and exercise a little bit up and down and get it to move to get it to seat in the correct location. So what you'll see normally is 1 to 4 exercises where you turn on and pressurize it with 10 PSI, pull a vacuum on it to return it, pressurize it, return it, pressurize it, return it, then go into a normal leak test. This is rather common when testing automotive clutches. Multi-channel testing, this starts getting a little different and a little strange on terminology. Multi-channel to different people means different things, okay? So a lot of times when we're talking multi-channel, do we mean sequential or do we mean concurrent? So what do I mean by that? Is on a multi-channel, would we consider this multi-channel? What this is, it's a pressure regulator, the fill and the isolation valve, the transducer, but we add 2 routing valves. This is really 2 sequential test channels. So what we're going to do is test part 1 first. When test 1 is complete, then we go on to test 2. But for some people, this is considered multi-channel because it's 2 different parts being tested in the same fixture or something along those lines. And normally these 2 programs are just tested in sequence. One of the things we see with multi-channel, what we really consider true multi-channel is we have a pressure regulator, our 2 valves, the pressure transducer and a test part, and a completely independent circuit for test part 2. We can do this on our Tecna T3L series with a 2-channel there, or we can do it with the TM3 series, but it's really 2 complete test circuits. So a lot of times routing valves and things like that get confused with being a multi-channel. Multi-channel to us is really independent testing. Dual channel, we can turn around and see what we would do is we pressurize 2 cavities at the same time, be able to do the leak test on this. They may have different test pressures. Tecna has a unique configuration using an electronic regulator that actually allows us to have 2 fill steps so we can test at 2 different pressures using 1 regulator. If we're looking at a single lumen catheter concurrent, what we can do is with our TM3 series, we're able to turn around and tie these all in independently and check 4 concurrently this way. 1 start signal, all 4 parts are tested. So an operator would load 4 parts, hit start, and off you go. Some of the things we see with multi-channel in automotive is like HP oil and water cavities, where we fill the oil, fill the water, settle and measure, okay? Usually oil and water are done at 2 different test pressures, okay? And one can finish before the other. One of the things Tecna has really got a specialty in for is multi-channel. We're able to actually do up to 16 concurrent test channels. Okay, but in this particular application, this is for a Chrysler cylinder head where we would do 4 intake runners, 4 exhaust runners, 4 spark plug tubes, HP oil and water all in the same test cavity, all with different test specifications. So these can all be run independently. This really speeds up cycle time and things like that, being able to run these concurrently. Okay. And that really takes us to the end of our presentation on pressure decay today. If we have any questions, now is the time for them. Feel free to go ahead and start asking those questions.
Hey, Gene.
Yes.
First question here is, you talked a little bit about plant temperature and how it affects the pressure decay method. How does the fluctuation in plant temperature affect testing, and how do you sort of handle that? How do you take care of that?
Well, the big thing with plant air temperature, there's a few different things you can do. As it varies throughout the day, I've seen some systems where they call it an auto comp, where you turn around and teach the tester a pressure change where it makes slight adjustments for background temperature and things like that. And one of the best ways of actually measuring temperature is actually doing a pressure change in the part itself, okay, and seeing how the part affects the change. So actually using the pressure sensor to measure what's going on in the part is a good way of doing that. So when you start seeing background temperature being an effect on it, you want to take a look and see what you can do to isolate that. Sometimes I've seen plants turn around and do where they do almost what we refer to as a poor man's temperature compensation. They turn around and set up two different test programs, one for operating between a certain temperature range and the other one for operating between a different temperature range. And you can set that up so the PLC controls it or something along those lines. But that's some of the things you can do with temperature. But temperature is definitely one of those things that you really need to take a look at what's causing the change.
Okay, got another one here, Gene. Does mass flow method fix the problems with pressure decay testing?
There's some real benefits to mass flow testing. And we'll take a look at that in another session with mass flow. A lot of times mass flow gets presented as a magic bullet, okay? But there's some trade-offs with cycle time and some other issues with that. So it's not always a better solution. We did recently have one customer that they had over 305 different part models, and they were trying to run them all on the same tester. And previously they'd been using a pressure decay system, and we moved them over to a mass flow system that allowed them to get down to 3 test programs and really improve repeatability, and they've eliminated their downtime to it. So mass flow definitely has its place. 15 years ago, I would have poo-pooed that idea, but I've seen some incredible stuff done with that. Any other questions? Then thank you for joining me today, and we're going to go ahead and conclude today's presentation. Thank you.